quick walkthrough through some of the ideas of fitting these psychometric curves with these sigmoid functions, these S-shaped functions. It's very convenient to use something called a cumulative normal distribution, so I want to explain to you where that comes from and what it means. Okay, so there's a little interactive demonstration here in this notebook, and so one thing I want to do is I want to load in some a summary of some psychophysical data. I've grabbed this from a text file that contains a little bit of information about a short experiment, psychophysical experiment I ran. The details here don't really matter, but the first column summarizes the properties of the stimulus, and in the second column, the proportion of times the subject said, in this case, the line was tilted more clockwise. So negative numbers here means counterclockwise, 0 means exactly vertical, and positive numbers means tilted slightly to the right. In this experiment, the subject had to say, on this presentation of this line, did it look tilted more clockwise? And you can see, even from this table of numbers, that when the line was tilted 10 degrees to the right, the subject said right 100% of the times, or the proportion is 1.0. If it was tilted to the left, they said it 0 times, 0% of the time. So that's where these numbers come from. Okay, so when we want to fit these data, we want to use an S-shaped curve, which is typically used in these kinds of settings, and it's very convenient to use a curve that can be controlled by two parameters. In this case, we're going to use a normal distribution curve that has two parameters, which you may remember from your stats class, a mean, mu, and a standard deviation, which is often called sigma. And so if we look at the top panel here, this is the curve you would have been used to seeing in your stats classes. This is a typical bell-shaped curve, a normal distribution. And if I change the mean of this curve, you can see it shifts this curve around. The standard deviation makes the curve taller or fatter in this particular case. Now, what you may not have seen as often before is the cumulative distribution function, which is related to this function at the top in a very particular way. So what connects those two things? The top curve, this probability distribution function, is this bell-shaped curve that you know from the stats class. The cumulative version is actually the area under the curve up to a certain point. So let me illustrate to you how this works. Okay, so if we imagine this cutoff point that I can map here, if we go to the location 0 here, where this curve has actually a mean of 0, so it's centered at 0, if we think about the area under the curve up to that point, that's half of the area underneath the whole point, and you can see that that translates into the value, or the y height of the cumulative distribution function on the second curve. Okay, so the area under the curve up to a certain point translates into the height of this curve, the cumulative version. And so the technical term for this is that this curve here is the integral of the curve above. Okay, so how is this useful? Well, if we imagine this data plotted with these symbols here, what we want to do is we want to find the two parameters mu and sigma that change the shape of the red curve in such a way that it fits as closely, as snugly to the data points as we can. Okay, so if I move this curve around a little bit, you can see that probably if I move it to here, that's probably going to be a good fit. And now I can adjust this other parameter, the standard deviation, which has an effect on the steepness of the curve, to find an optimal value to fit the curve. Okay? And so I'm doing this here by hand to illustrate to you how these parameters change the shape of these functions. But of course, we want the computer to do this for us. So in real life, or when we code this up, we let the computer find the optimal parameters mu and sigma in an iterative process, which is called, and the general idea is called it's nonlinear least squares. Okay, so we start with a guess for what these parameters should be. So maybe you think it's a reasonable assumption that the mean of your data should be around 0 and the standard deviation should be 1. And then we hand over the problem to the computer, to an algorithm, to find the values that actually best fit the data. And in MATLAB, this can be done with LSQ curve fit, as I will show you in code later.